Welcome. In this session we will look into how to solve linear programming problems using simplex method. So, in a linear programming problem the objective function is linear and the constraints are also linear. So, in this case the decision variables are x1, x2 all the way up to xn. So, here we can have equality constraint as shown over here. Here we can have greater than or equal to constraints and also less than or equal to constraints, right. So, this qualifies to be a linear programming problem. The only requirements are the variables need to be continuous and the constraints need to be linear. So, this can also be compactly represented as this one, right. So, all the greater than or equal to constraint can be converted into less than equal to by multiplying by a minus sign. So, this will become less than equal to minus B2. So, in this case C will be C1, C2 all the way up to Cn, x would be x1, x2 all the way up to xn, right. So, that when we do C transpose x we get this equation. So, A in this case would be a matrix. So, it will have the coefficients involved in the inequalities, right, whereas B is the right hand side value of the inequality constraints. A equality would be the coefficient matrix of the equality constraints and B equality would be the right hand side value of the equality constraints. Over here the variables x can have their own lower bounds and upper bounds. So, a large number of optimization problems can be formulated as linear programming problem. Some of the applications are in resource allocation, production scheduling, workforce planning, transportation among others. A mathematical property of linear programming formulation is that at least one optimal solution will lie on one of the vertices of the feasible region. So, for example, we have these constraints, constraint 1, 2, 3 and 4, and this shaded region is the feasible region. So, for this problem it is guaranteed that the optimal solution will lie either at this vertex A or at this vertex B or at this vertex C, this one or this one or this one. So, the optimal solution is guaranteed to lie at one of these vertices. So, the method which we are going to discuss is simplex method. So, the simplex method is designed in such a way that it explores only the vertices, right, and when it moves to one vertex to the other vertex it is ensured that the vertex which is being currently visited is better than any of the previously visited vertices. So, simplex method was developed in 1947 by George Dantzig for solving optimal resource allocation problems, right. So, the method is designed to handle large number of decision variables and constraints. So, it solves for the optimum solution by visiting the vertices of the feasible region. So, to apply the simplex method as discussed in this course, right, we should have an objective function which needs to be maximized. So, if we have a minimization objective function it has to be converted into a maximization form, right, and all the constraints should be expressed in less than equal to form, right. So, Ax less than equal to B, right. So, if there are constraints which are greater than or equal to, we can multiply by a minus sign and bring it in a less than equal to form, and all the decision variables should be non-negative, right. So, remember linear programming does not require all the decision variables to be non-negative, but the way we are discussing simplex method requires the decision variables to be non-negative and the right hand side of the constraints should be non-negative. So, the right hand side of the constraints are these one B1, B2 till Bm, those should be non-negative. So, we need to ensure these four things, right. So, as discussed we require the objective function to be in the maximization form, right. If we have an optimization problem which is to minimize z, then instead of minimizing z if we maximize minus z we will get the same solution, right. So, for example, over here if the objective function is minimize 5x1 plus 4x2, then instead of minimizing this we can convert it into an equivalent maximization problem wherein we maximize minus of 5x1 plus 4x2, right. So, this is how we can convert the objective function into the standard form that is required. If there are less than equal to constraints, right, we add slack variable on the left hand side and convert it into an equality constraint, right. So, over here if we see we have this equation x1 plus 2x2 is less than equal to 10. So, we want to convert this equation into an equality constraint, right. So, this 10 stays, x1 plus x2 stays, right. So, since this is a less than equal to, we add a positive variable, let us say S1, right, so that it becomes an equality constraint. That is what is given over here, and the slack variable need to be positive, right. If we are given a greater than or equal to constraint, we can subtract a positive variable known as surplus variable, right. So, for example, here we have 3x1 plus 2x2 greater than equal to 11, right. So, this equation can be written as, so S1 has to be positive, right, equal to 11. This is how we can convert a greater than equal to constraint, right. So, one other requirement which we had was that the right hand side value of the equation should be non-negative, right. So, for example, if we have this 3x1 plus x2 is equal to minus 11, then what we can do is multiply by a minus sign on both the sides, right, so that the right hand side becomes a positive value. If there are negative variables or unrestricted variables, so remember the standard form that we want is maximize, let us say C transpose x, right, subject to all the constraints we would require in this form, less than equal to form, right, and the variables need to be greater than or equal to 0. So, the way we are going to discuss simplex method is applicable only for this problem, right. So, simplex method requires the variable to be positive, but linear programming does not require the variable to be positive. So, the linear programming can have variables which are unrestricted or can take both positive and negative values, right. So, in that case what we do is that to convert that linear programming problem into a form that is compatible to simplex, we will replace each unrestricted variable by the difference of two other variables, right. So, for example, let us say 3x1 plus x2 is less than equal to 9, and let us say over here x1 is a variable which is unrestricted, right, and x2 is greater than 0. So, what we will do is we will replace x1 by the difference of two numbers, x1 prime and x1 double prime, right. So, these two numbers are positive, their difference can be negative, right. So, wherever we have x1, we replace it by x1 prime minus x1 double prime. Since this is a less than equal to constraint, we add a slack variable to make it as an equality constraint. So, this problem is something that we have discussed previously. So, there is a paint company which can manufacture exterior paint as well as interior paint. So, the profit per unit of exterior paint is 5, the profit obtained per unit of interior paint is 4. So, both the paints require raw material M1 and M2, right. So, exterior paint requires 6 units of M1 and interior paint requires 4 units of M1. The total amount of raw material M1 that is available is 24 units. Similarly, for exterior paint and interior paint we require raw material M2 and the quantity required is 1 unit and 2 unit respectively. The total amount of M2 that is available is 6 units, right. So, we have additional two constraints, right. So, one is that daily demand for the interior paint is 2 units and demand for interior paint cannot exceed that for exterior paint by more than 1 unit. We will not discuss into this formulation, we have discussed this previously. So, these are our 4 equations 1, 2, 3 and the fourth one over here. These are bounds on the decision variable x1 and x2. So, the optimization problem is to maximize profit. X1 and x2 are our decision variables. X1 denotes units of exterior paint produced daily, whereas x2 indicates the units of interior paints produced daily. This problem is now to be transformed into the standard form required for solving using simplex method. So, in simplex method the objective function as well as the constraints are required in algebraic form. This equation can be written as z minus 5x1 minus 4x2 equal to 0. Over here, as we discussed earlier, for less than equal to constraints we can add slack variables. This equation is not in the required form. So, we convert it into first into minus x1 plus x2 is less than equal to 1 and then add a slack variable s3 to make it as a equality constraint. Similarly, this constraint x2 is less than equal to 2, we can add a slack variable s2 plus s4 is equal to 2. So, now we have 4 slack variables, right, and 2 decision variables, right. So, our decision variables are 2, since we have 4 constraints of the form less than equal to, we added 1 slack variable for each of the constraint. So, we have now 6 variables. So, z is not to be considered as a variable. So, we have 6 variables over here. So, the number of variables is 6 and the number of linear equalities which we have is 4. So, 1, 2, 3 and 4. So, 6 minus 4 is equal to 2. So, we have 4 basic variables and 2 non-basic variables. Right. So, 4 basic variables are S1, S2, S3 and S4. The 2 non-basic variables are x1 and x2. So, an initial solution for this problem is, if we take x1 equal to 0 and x2 is equal to 0, right. So, this equation will give us the value of S1 to be 24, the second equation will give us the value of S2 to be 6, the third equation will give us a value of S3 to be 1, and the fourth equation would give us the value of S4 to be 2, right. So, these two are non-basic variables, right, whereas these 4 are basic variables, right. This solution satisfies all the constraints, right. So, for this solution the objective function is 0. Now, we have this 0 comma 0 as the initial starting point. So, this figure over here shows a graphical representation of this problem, right. So, here we have two variables. So, this is x1 and this is x2. So, if you remember, we can plot all of these lines. So, if we take the first equation 6x1 plus 4x2, right. So, let me write it as equal to 24, right. So, in this equation if we substitute x1 is equal to 0, we will get the value of x2 to be 6. So, the first point is 0 comma 6, which is over here. To get the second point, we can put x2 is equal to 0. So, this will give x1 is equal to 4. So, we will get this point, right. So, we can draw this. So, this is the line which is 6x1 plus 4x2 is equal to 24. So, the feasible region is below it. So, let us take the point 0 0. So, 0 comma 0 will satisfy this constraint. So, this point is a feasible solution, right. So, the feasible region for this particular constraint is all of this, right. So, similarly we can plot the other two constraints. So, the common feasible area corresponding to this constraint, first, second constraint, third constraint and fourth constraint is the shaded region. So, simplex method is designed in such a way that it will only visit the vertices, right. So, though we have such a big feasible region over here, simplex method is only going to visit the vertices. So, this is vertex A, B, right. So, we have another one over C, D over here, E and F. The optimal solution is located at one of these vertices, and the simplex method itself is designed in such a way that it will only visit this vertices. It is not going to explore anywhere inside this feasible region. So, now we have this algebraic form over here. Let us construct what is known as the simplex table, right. So, these are the 6 variables which we have now. X1 and x2 are non-basic variables, and S1, S2, S3, S4 are our basic variables, right. So, this is basic variable, this is non-basic variable, and this column is the right hand side which we have for all of this equation, right. For each of this equation there will be a row in the simplex table, right. So, for the first equation, if we see the coefficient of z is 1, right, the coefficient of x1 is minus 5, the coefficient of x2 is minus 4, and this equation does not involve s1, s2, s3, s4, or it is equivalent to 0 s1 plus 0 s2 plus 0 s3 plus 0 s4, right. So, we write zeros over here and the right hand side is 0, right. So, in the next row the basic variable is s1. So, there is no z which is involved over here in this equation. So, the coefficient of z is 0, the coefficient of x1 is 6 and x2 is 4, right, and it involves only the slack variable s1. So, the slack variable s2, s3, s4 are not involved in the first equation. So, we have zeros over there, and this right hand side is 24. So, the second row is for this equation. So, here the basic variable is s2. So, we write s2 over here. The coefficient of s1 is 0, the coefficient of s2 is 1, s3 and s4 are not involved, the right hand side is 6, and the coefficient of x1 and x2 are 1 and 2 respectively. It does not involve z. So, we have a coefficient of 0. Similarly, we write for the next equation. So, here z is not involved. So, the coefficient of z is 0, s3 is the slack variable over here, or that is the basic variable, and the coefficient of x1 and x2 are minus 1 and 1. So, coefficient of x1, x2 is minus 1 and 1, and the equation does not involve s1, s2 or s4. So, their coefficients are 0, it involves s3. So, its coefficient is 1 and the right hand side value is 1 over here. So, similarly, we can also write the next equation, right. So, the next equation involves only x2 and s4. So, we have the coefficient 1 1 over here, rest of all the coefficients are 0, and the right hand side over here is 2. So, we write the 2 over here. This completes the construction of the initial simplex table. So, now we will look into certain terminologies and rules to be followed for simplex table. Simplex method is an iterative method. So, the question is, when do we stop the method, right. So, the method is stopped when we attain the optimality criteria. So, the optimality criteria is attained when the coefficient of the non-basic variable in the first row are non-negative, right. So, here if we see these two are our non-basic variables, right, whereas these 4 are our basic variables. The first row is the equation that we had from the objective function, right. So, the coefficient should be non-negative. Right now we have -5 and -4, right. So, that means that we have not reached the optimality criteria. So, since x1 and x2 are not over here, so they are non-basic variables and their value is now 0, 0, right. So, the value of s1, s2, s3, s4 is 24, 6, 1, 2. The value of the objective function is 0 and the value of x1 and x2, as they do not appear in the basic variable and they, since they are non-basic variable, their value is 0. So, if we see this plot, we are currently at this point. So, the starting point of the simplex method is this point, which would be a feasible solution. Next we have something called as entering basic variable. So, entering basic variable is the variable which has the most negative coefficient in the first row, right. So, for example, now in this first row we have -5 and -4 over here. So, -5 is the most negative. So, this is called as entering variable, right. So, this variable which is a non-basic variable will now become a basic variable. Pivot column is the column of the entering basic variable, right. So, here we had identified that x1 is the entering variable, right. So, since x1 is the entering variable, the column corresponding to x1 is the pivot column. So, once we have identified entering variable, the pivot column, now we need to identify something called as pivot row. So, to determine the pivot row, we need to first find out the term ratio. So, ratio is the right hand side value, whatever is written solution over here, divided by their corresponding coefficient in the pivot column. So, over here 24 is the value and its corresponding coefficient in the pivot column is 6. So, 24 by 6. So, here it is 6 by 1, here it is 1 by -1 and here it is 2 by 0, right. So, if we calculate, it comes out to 4, 6, -1, infinity, right. So, that is how we determine ratio. Once we have determined the ratios, we need to determine the pivot row. Pivot row is the row which has the minimum positive value. So, in this case, if we see, 4 is the minimum positive value in this column, right. So, that row corresponds to the pivot row. So, first we identified the entering variable. So, entering variable was the one which had the most negative coefficient, right. Its corresponding column is the pivot column. Then we calculated the ratios. Ratio is the right hand side values divided by the corresponding element in the pivot column. So, that will give us the ratio, and the minimum positive value in the ratio helps us to identify the pivot row. So, now once we have identified the pivot row, the basic variable corresponding to the pivot row, so in this case which is S1, so that is the leaving variable. So, first we identified entering variable, now we have identified the leaving variable, and the intersection of the pivot row and pivot column, so this element is the pivot element. Once we have identified the entering variable, leaving variable and the pivot element, we need to include the entering variable into the basic variables and remove the leaving variables. So, for example, if we see x1 is the entering variable over here, right. So, x1 enters as a basic variable, whereas s1 is removed from the basic variable. So, s1 which was here is no longer in the set of basic variables. So, this remains. So, we do not make any changes in this x1, x2, s1, s2, s3, s4. It is just that one of the non-basic variables will become entering variable and one of the basic variables will become the leaving variable, right. So, first was to identify entering variable, leaving variable. Once we identify entering variable and leaving variable, we will know the pivot element. Once we have identified the pivot element, we bring in the entering variable into basic variable and remove the leaving variable from the basis vector. So, the next step is to determine the next feasible solution. So, to determine the next feasible solution, we need to divide the pivot row by the pivot element, right. So, over here this is the pivot row, this is the pivot element. So, we need to divide this entire row by the pivot element, right. So, 0 by 6, 6 by 6, 4 by 6, 1 by 6, 0 by 6, 0 by 6, 0 by 6 and 24 by 6, right. So, that is what we get the new row. So, now that we have made the pivot element as 1, the next step is to make other elements in the pivot column as 0 by appropriate row operations. So, this can be implemented using this, right. A new row is given by its corresponding current row minus the corresponding pivot column coefficient multiplied by the new pivot row, right. So, our new pivot row is 0, 1, 4 by 6, 1 by 6, 0, 0, 0 and 4, right. So, let us see how to do it for the first row. So, the new row corresponding to Z is the old row corresponding to Z, right. So, which is 1 minus 5 minus 4, 0, 0, 0, 0, 0. So, that is what is written over here, minus the pivot column coefficient, right. So, we are operating on this row, right. So, for this row the pivot column coefficient is minus 5, right. So, we write that minus 5 over here multiplied by the new pivot row. So, in our case the new pivot row is the pivot row corresponding to x1, right. So, the elements are 0, 1, 4 by 6, 1 by 6, 0, 0, 0 and 4. So, that is what we have written over here. Similarly, we can calculate the new row S2, right. So, the new row S2 is the old row S2 minus the corresponding pivot column coefficient. So, that is 1 in this case multiplied by row of x1. So, that is how we get row S2. So, similarly, you can find out the row corresponding to the basic variable S3 and the row corresponding to basic variable S4, right. So, this table which we had before the row operation will get transformed into this table. So, in this case if we see, except for this pivot element 1, all the rest of the elements are 0. So, this completes the first iteration of simplex method. So, now that we have completed the first iteration of simplex method, we need to check for the optimality condition, right. So, optimality condition is that the coefficient of non-basic variables should be non-negative. So, out of the 6 variables which we have, x1, x2, s1, s2, s3 and s4, right, x1, s2, S3 and S4 are basic variables. So, the two non-basic variables are x2 and s1, right. So, this x2 and s1, these are non-basic variables. So, we need to look into their coefficients in the first row. So, their coefficients in the first row, if they are non-negative, then we have reached the optimal solution. So, in this case we have not reached non-negative values. So, this is a negative value, right. So, still we have not achieved the optimality, right. So, we need to perform the second iteration of simplex method. So, now if we see, initially we were at this position, right. So, at the end of first iteration what we have is the value of x1 is 4, right, and x2 does not appear in the basic variable, right. So, the value of x2 is 0, right. So, 4 comma 0 is the new solution that we have at the end of iteration 1. The objective function value corresponding to this 4 comma 0 is 20, right. So, 4 comma 0 is shown over here. So, initially we were at this 0 comma 0, right, at the beginning of the first iteration, right. So, from vertex A we have moved to vertex B, which is 4 comma 0. So, the next iteration will take us to one of these other vertices. So, for second iteration of simplex method we need to repeat the same procedure, right. So, over here we have the same table which we got at the end of first iteration, right. So, in this case the most non-negative is minus 2 by 3, that corresponds to x2. So, that column becomes the pivot column and x2 is the entering variable. So, we have identified the pivot column. Now, we need to identify the pivot row. So, to identify the pivot row we need to divide this column by the pivot column, right. So, these are the ratios which we have. To identify the pivot row we need to look for the minimum positive value, right. So, the minimum positive value over here is this 3 by 2, which is 1.5, right. So, that is the minimum. So, the row corresponding to it is the pivot row, right. So, now we have identified the pivot column, we have identified the pivot row. So, this intersection of pivot row and pivot column is our pivot element. So, this pivot row corresponds to the basic variable S2. So, now S2 will become the leaving variable, right. So, now we have identified the entering variable and we have identified the leaving variable. Now, we need to make this pivot element as 1, right, and all the other coefficients in the pivot column should be 0, right. So, the entire row operation has to be repeated. So, x2 is the entering variable and s2 is the leaving variable, right. So, over here we replace s2 by x2 and this x2 remains the same, right. So, remember the leaving variable is not to be written over here. This set of variables over here remain as such, just that the leaving variable is no longer a basic variable, whereas the entering variable becomes a basic variable. So, now that we have made this entering and leaving variable, we need to now make this pivot element as 1, right. So, to make that pivot element as 1, we need to divide this entire row, the third row or the row corresponding to the basic variable S2 by 4 by 3. right. So, if we divide it by 4 by 3, we would get it as 0 0 1 minus 1 by 8 3 by 4 0 0 3 by 2. Once we have made the pivot element as 1, we need to make the rest of the entries in the pivot column as 0. So, again we employ the same operation. The new first row is the old first row minus the corresponding element in the pivot column, which is minus 2 by 3 over here, multiplied by the new pivot row, right. Similarly, the new row corresponding to x1 is the old row corresponding to x1 minus the corresponding element in the pivot column. So, in this case the corresponding element in the pivot column is 2 by 3. So, this 2 by 3 multiplied by the new pivot row, right. So, the new pivot row is 0 0 1 minus 1 by 8 3 by 4 0 0 and 3 by 2. So, similarly we can get row 3 and row 4. So, if we perform this operation, this table will get transformed into this one, right. So, this completes the second iteration. If you remember, when we started with this first point, then we moved to this point, right, and then now we have achieved this point. So, this point, because the value of x1 is 3 and the value of x2 is 3 by 2, right. So, this point corresponds to 3 comma 3 by 2, right. So, that is the point which we are currently at, right. The objective function at this point 3 comma 3 by 2 is 21. So, we have completed the second iteration, right. So, we have moved from this point to this point, now we have come to. So, in this case it happened that we are moving from point 1 to point 2 to point 3, right. So, if you see, we have only visited the vertices. So, our initial simplex table corresponds to this 0 comma 0, the second solution which we had corresponded to 4 comma 0, the third solution which we have at the end of second iteration corresponds to 3 comma 3 by 2, right. So, before proceeding for the third iteration, we need to check whether we have reached the optimal solution or not, right. So, for that we need to check the coefficients of the non-basic variable. So, our variables are x1, x2, s1, s2, s3 and s4, right. Among this x1, x2, s3, s4, x1, s2, s3, s4 are basic variables. So, now our non-basic variables are s1 and s2 and their coefficients are positive, right. So, since their coefficients are positive, we can confirm that 21 is the optimal solution corresponding to x1 is equal to 3 and x2 is equal to 3 by 2. Now that we have solved it, right, the simplex table not only gives us the value of the decision variables, right, but also gives certain additional information. So, this is the optimization problem which we started with, right, to maximize 5x1 plus 4x2, right, and the constraints were 6x1 plus 4x2 is less than equal to 24, x1 plus 2x2 is less than equal to 6. So, if you remember the context of this problem, these two indicated the amount of raw material 1 and 2 which were available, and then we had this requirement about the quantity of interior paint and exterior paint that is produced, and we had this demand constraint wherein we were not allowed to produce more than 2 units of interior paint, right. So, this problem we had transformed into this form wherein we got all the constraints to be in the less than equal to form, and then from this optimization formulation we went to this algebraic formulation which satisfies the requirement of simplex method as discussed in this course, right. So, the objective function was to be maximized, the right hand side of the equations should be positive, and we added slack variables which are also positive. So, we added this 4 slack variables since we had 4 constraints and all of the slack variables are positive. So, this is what we solved, and after 2 iterations we ended up with this table. So, in this table we know that x1 is equal to 3 and x2 is equal to 1.5. So, x1 is equal to 3 and x2 is equal to 1.5, and at this point x1 is equal to 3 and x2 is equal to 1.5, the profit that we would be making is 21 units. So, this is the information which is what we sought out for the optimal values of the decision variable and its corresponding objective function, right. But we can also see that the value of S3 and S4 is 5 by 2 and 1 by 2, right. So, the value of S3 is 2.5, 5 by 2, and the value of S4 is 1 by 2, and since S1 and S2 do not appear over here as basic variable, their values are 0. Now, let us look at what do these values signify, right. So, S1 was related to the first constraint and S2 was related to the second constraint, right. So, in this equation at the optimal solution this is 0 and this is 0, right. So, that means the entire quantity of raw material 1 and 2 which are available are utilized, right. So, if you want to check that, what we can do is 6 into 3 for this constraint plus 4 into 1.5, this is equal to 24, which is what we have on the right hand side, right. So, the slack variable is 0. So, that is what it indicates, that for the amount of paint 1 and paint 2 that we are producing, we are utilizing entire 24 units. Similarly, for the second slack variable S2 is also 0, right. So, let us look into this constraint, x1 plus 2 x2 is less than equal to 6. So, x1 is 3 plus 2 into 1.5. So, this happens to be 6 and the right hand side is also 6. So, since S2 is equal to 0, we can directly say that the entire quantity of 6 is being used. So, that is why we have these two remarks over here, complete utilization. So, similarly for S3 and S4, right. So, these equations would be satisfied. So, minus x1, so minus 3 plus 1.5 plus S3 is equal to 1. So, this equation would be satisfied only when S3 takes a value of 2.5. Similarly, for the final constraint, so x2 plus S4 is equal to 2, this constraint over here. So, x2 is currently 1.5. So, we can even add 0.5 to meet this constraint, right. So, what it basically means that even if we decrease this 2 to 1.5, right, the optimal solution would not change, right, because x2 is anyway 1.5, right. So, even if market demand were to reduce for paint 2, right, there will not be any change in the optimal amount of x1 and x2 that has to be produced. So, the simplex method which we have discussed is the basic simplex method, right. There are several other considerations that we need to take care of. So, in simplex method we might encounter these 4 different cases, right. One is degeneracy. So, this happens when there is a tie in the minimum ratio test. So, remember, once we have identified the pivot column, to identify the pivot row, we had to do the minimum ratio test. So, it might happen that 2 values in that particular column can be identical. In that case, we can take any one of them and continue, right, but at times it can lead to iterations which do not necessarily improve in the objective function values. Another issue that can occur in simplex method is when we have alternative optima, right. So, over here what happens is that the objective function is parallel to a non-redundant binding constraint. So, the solution lies on the constraint and this constraint is parallel to the objective function. So, just like we drew the constraints, we can also draw the objective function, and if it happens that the objective function is parallel to a non-redundant binding constraint, in that case we have alternative optima. The other circumstance is when we have unbounded solution. So, under this circumstance the solution space is unbounded for at least one decision variable, and if the constraints are inconsistent, right, if they are conflicting one another, then there would be no feasible solution. So, in such cases we need to employ special strategies for simplex method. So, we can also encounter ill conditioned simplex. So, for the discussion whatever we had done so far, we had assumed that we will be able to convert all the constraint into less than equal to form, as well as the right hand side would be a positive value, right. Additionally, we did not look into the constraints, let us say which is greater than or equal to 5. If we convert this greater than or equal to constraint into a less than or equal to constraint, we end up with a minus 5, right. So, now the right hand side is no longer a positive value. In that case, we cannot directly employ the simplex method which we have discussed. Additionally, if we have equal to constraints, so let us say x plus y is equal to 18, right. So, we did not consider constraints which are of this nature, right. In these two cases, when we have a greater than or equal to constraint and equality constraint, we need to introduce additional artificial variables, right, just like we introduced slack variable, right, and then we will have to employ either a big M method or a two-phase method to solve such problems. So, that is something that we have not discussed in this course. The problem which we solved is known as the primal problem. Given a primal problem, we can also construct a dual problem. The solution of this dual problem and the primal problem would be identical. In many circumstances, it is better to solve the dual problem rather than the primal problem. So, conversion of primal to dual is something that we have not done as part of this course, and we can also do a sensitivity analysis. Over here we did only preliminary sensitivity analysis, right, as in like when we had values of the slack variables at the end of the simplex procedure, we interpreted what do they indicate. So, the sensitivity of the solution can also be studied with respect to various other factors. That is something that we have not done as part of this course, right. For all this you can look into any standard book of optimization. One of them is by Taha and the other one is by S.S. Rao. With that we will be concluding this session on linear programming using simplex method. In the next session we will be looking at branch and bound method to solve mixed integer linear programming problems. Thank you.